Hello everyone, and welcome to today's seminar. I'm going to be your host today since we don't have no one to town. So my name is Benji, and I'm super interested to be here and be your host. We have exciting presentation lineup for today by Ian on seismic response of non-structural platform frame, cold frame, steel walls, and its drift compatibility. Ian is a PhD student here at the Department of Civil Engineering and has done a quite fascinating job on this topic. So without any further ado, Ian, the floor is all yours. Go ahead.
So thank you for introduction. Good afternoon, everyone. I'm Ian. So today I'm going to talk about the topic seismic response of non-structural platform frame cold steel wall subassemblies detail for drift compatibility. So this is a brief outline of what I have planned for today. So first, I will introduce the topic of research and explain the motivation behind it. Second, I will explain the experiment test for this research, including a brief introduction of the 10-story test program and the detail of platform frame subassemblies, the exterior CFS1 and interior walls. After that, I will report the findings from the experiment, and last, I will give a brief conclusion and the future work. So now I will start to introduce the CFS frameworks. So CFS is common building material with these advantages. The first, cost-effective, durable, sustainable, non-combustible, and resilient. And most of all, these are easy to install. So CFS is widespread in commercial buildings, and it may be used for both structural, such as the CFS shear walls, and non-structural components. And today, we will just discuss about the non-structural CFS walls. And this slide shows the typical framing configuration of platform frame CFS walls. The wall consists of tracks at the top and bottom. So at the top here, top track, bottom track, and the stud frame to length. Okay, and here is the concept of installing the CFS non-structural walls. So first, we'll attach the top and bottom track to the upper and lower slab. Then next, we'll connect the end stud and the jambs to the track. The jambs might be thicker than the typical stud because of the openings. Then after we connect the jambs, header and seal will frame into the jambs. And after that, we will screw all the studs into the tracks. So these are the CFS framing. Then last, we'll cover these framing by gypsum board on both sides. Okay. So however, as we discussed, CFS walls were floor-to-floor systems, which are significantly sensitive to the interstory drift. The figure at the left here shows that when the wall subject to the interstory drift, the wall start to deform and getting damaged. Porter et al. 2001 here shows that the wall might start minor damage at interstory drift ratio of 0.3%. And the significant damage start at 0.5%, just like here 0.5%. And when the interstory drift get to 1.5% here, all the walls will appear significant damage. So the damage to non-structural wall is a large portion of cost associated with earthquake damage. Furthermore, we cannot use a building where all the walls have fallen down. So what we want is that the building to be able to recover as quick as possible after an earthquake. So that means the walls need to either avoid these damage or easy to repair after an earthquake. So here is one way to avoid the wall deform. The horizontal joint were used at the top of the wall. And these horizontal joint can isolate walls from the upper slab, preventing the wall getting deformed and damaged. However, these the slip mechanism might cause issue where the wall intersect. Typical wall details are unable to separate the corner here. So when here is the implant implant movement, so the corner will just tearing and crushing a layer. And some of the research have been able to limit this damage at the corner by placing gap here. But these prevent the onset of damage until the gap closed. So after the gap closed, the corner will still getting damaged. So here are the gaps in current research. First, the damage mitigation mechanism have been proposed but not improved significantly. And second, no research on non-structural exterior walls and limited research on shelf walls. And fourth, the incompatibilities at the corners. And five, most of all, there's lack of the full system testing. So now I will introduce about the 10-story shake table test building. And we have put our walls in this building. So the test building was a full-scale 10-story mass timber building at UC San Diego outdoor shake table. As far as we know, this is the tallest timber building that had ever tested on a shake table. So the building used mass timber post-tension rocking walls, which are able to accommodate larger without damage. So non-structural systems need to accommodate those strips as well. Thus, non-structural systems were designed to accommodate 2.5% interstorage drifts. And this slide shows that all the non-structural assemblies that were installed into the test building. And today we'll just focus on the CFS1 on the west-south side of the building and the interior partition wall on level 4 to 6. So in this test, two types of design horizontal joint were installed at the wall. One is double slip check here, and the other is the studded slip check. So the first double slip check, just as it was, there are two tracks at the top of the wall. The outer track attached to the slab and the inner track sit in there. So this is the inner track and outer track attached to the slab. So the upper track flange restrict all of plane motion while allowing the in-plane movement. Then the gap between both tracks, these here, can accommodate the vertical movement. However, the construction detail that need to be careful is that the sheeting screw, the black sheeting screws here, should not screw too high through the outer and inner track. So if it screws through the outer and inner track, it will prevent these two track slip. Another type of track is studded slip check. So there are slots at the webs and the flange. The horizontal slot at the web allows the in-plane movement, while the vertical slot at the flange allows the vertical movement. And the construction details for this type of track is that we should not screw these screws too tight to the slab to prevent the track to slip. Then to accommodate the incompatible movement at the corner region, a vertical joint were installed. So the gap at the corner was filled with a rubber gasket joint. A rubber cover was held in aluminum extrude frames. And here are the comparison of the typical interior walls and the CFS exterior walls. And first, exterior walls need to resist wind load. So the section size are usually larger and thicker. So in our project, our interior wall section use 3 and 5/8 inch deep section, while the exterior wall use the 6 inches section. And likewise, the sheathing and fastener on exterior walls are usually more robust. Additionally, the exterior sheathing of exterior walls use stronger fiber mat sheathing products. Second, the exterior wall have additional component for resisting the element. So the exterior face can be clad with a variety of material that might add a lot of mass of the exterior walls. So in our case, we have used the moisture barrier and a lightweight ACM panel on the exterior side. So this slide shows the elevation view of CFS1. And here is the west view and south view. And we installed a double slip check on story 1 and 3. So these two stories is double slip check. And the solid check on story 2. And for the gasket joiner, we just installed on story 1 and 2. And on story 3, the corner served as a control and no special joint here. So the gasket joint at the corner, and here is the no special joint. And the next is the comparison of the conventional interior walls and the shelf walls. So different from the conventional walls, shelf walls were designed as a 2-hour fire rated wall. So the interior side of shelf wall, we use 1-inch thick shelf liner. And on the exterior side of shelf wall, we install 2 layers of gypsum board. So these are the plan view, the wall layouts for interior walls. And story 4 and 5 are represent the residential floor plan. On story 4, interior partition wall that extend to the shelf wall assemblies in all directions. So here, so these are wall 6, 7, 8, 9, 10 is the conventional wall, 11 to 14 is the shelf wall. And story 5 had a similar layout to story 4, but the shelf wall for this one is a stair built-in shelf wall. So the shelf wall is stair built-in, and these are all conventional interior walls. And beside the resident floor plan, 2 independent walls, the C-shaped wall, this one, wall 15, and a T-shaped wall, wall 16, were installed on level 6. And for interior walls, 3 types of expansion joints were used to accommodate the incompatibility at the corner region. The first one is the FWFC 600 gasket joint. This joint is similar to the SF series used to the exterior walls. The rubber gasket fit into the extrude aluminum frames. The second one is the fire barrier. At the intersecting corner of the shelf wall, the fire rating of shelf wall should be maintained. So the fire barrier will insert into the gap. And there are some standard corner detail were applied at other locations for direct comparison to these innovative solution. And on story 6, a different type of expansion joint, AFWC 400 expansion joint, which has formed aluminum cover plate that fill over extrude aluminum frames, were installed on level 6. So here are the joint locations. So for FWFC 600 is on wall 8, wall 9 on story 4, and 3, 4, 5 on story 5. And the fire barrier is at the corner of the shelf wall. And on story 6, we install the AFW and AFWC 400 expansion joint. Then after install all the walls, the building were subject to ATA ground motions with uniaxial, the X direction with the east and east-west direction, the north-south direction we call Y direction, and biaxial direction, and 3D motions. And these ground motion can characterize into 5 hazard level from 43-year return period to MCER shaking intensities. And the test number will from mid 13 to 100. And there are some sensors installed into the building. So the first is we want to get the interstory drift for the buildings. So we have installed a accelerometer on the floor slab and the interstory string path across the story. And for our non-structural walls, string path between the walls and the building were installed to measure the wall slip, and the string path across the expansion joint to measure the joint drift. So to compute the interstory drift, we need to use the displacement of the adjacent stories. Thus, the structural floor displacement is significantly important. So here is the process how we get the floor displacement from double integrating the floor accelerations. Then after getting the interstory drift, the drift reduction was used to evaluate the performance of each slip detail wall during the test. The drift reduction will calculate as 1 minus the ratio of peak wall drift over the peak interstory drift and times 100%. So that means a higher drift reduction indicates that the wall experienced more slip, which in turn reduce the transfer of interstory drift to the wall. So now I'm going to discuss about more details about CFS1. So here is the elevation view that I just showed. And this slide shows the construction for the framing. Like screw the top track first and the jambs, then the headers and the seals. And here is the finished framing. And finish the framing, we install the gypsum at interior side, the glass mat on exterior side, the black waterproofing paint layer, and then ACM panels. Then for the expansion joint, we leave a 6-inch gap. So here is a 6-inch gap. Then install the rubber gasket into it. So now let's look at an earthquake. So here, this one is the CFS1. So the story 1 and 3 did not slip much. That we will discuss later. So we can focus on the top of story 2 and at the corner, the expansion joint at story 2 here. So we can see the story 2, the wall slips. And this one is a view from interior side with the same motion. And here is the story 2. Yeah. So now we use the drift reduction equation to evaluate the exterior walls. So in this figure, we can see that the study slip check for story 2, the L2S can slip around like the drift reduction is around 25%, and the L2W can get up to like 70%. But for the double slip check on level 1 and 3, they are all lower than 10%. Yeah. So these are the factors that prevent slip. So the first is the friction force between two tracks were larger than expected. So that means not enough drift demand to activate the slip mechanism. And at some place, we found that the sheathing screw through the both track. So that might prevent a little bit of the slip. But the wall did not slip as expected, but there's no significant damage was found on the wall. And the cause of it might be because the wall were not fully finished and the panel rocking mechanism accommodates some of the drift. And here shows the panel rocking mechanism. The panel rock relative to one another, and this video shows that. So from CFS1 lab, we learned that the double slip track did not slip as expected in these tests. And second, the panel rocking mechanism accommodates some drift. But if the wall were finished, the crack between the panel might occur. And the third, no damage on the wall. That means the specimen was not tested to its limit state. Then next, I will give a detail about the interior walls. So here the same view, the wall layouts of interior walls. And here is the construction for the conventional walls. And it's different from exterior wall, just we have mud and tape the gypsum gap after we install all the walls. And here is the construction of the shelf wall. The shelf liner board was friction fit into the interior side of the wall. So the stud and gypsum panel could slip relative to the top track in the in-plane direction because there's no screw or screw at the top of the track. So the video shows how we construct the shelf walls. So we just fit the shelf liner into the stud, and we didn't use any screws at there. After fit the shelf liner in there, and another stud will fit into it. But however, there are some special details for installing interior walls. The first is that we connect the shelf wall and conventional wall on story 4. So the top track flange conflict at the connecting region just here. So this part is shelf wall, this part is conventional interior walls. So we need to cut 5 inches flange to prevent the stud from colliding with the track flange. Okay. The second is on story 5, wall 2 and wall 4, these two walls. These two walls just sit right beside the beams that restrict access. So the walls were pre-constructed on the floor and then moved into the place. And for the fire barrier on story 4, the fire barrier was 12 inch wide and needed to be squeezed into the 4-inch gap. So the contractors was unable to do that. So our research team managed to install the fire barrier, but just after cutting 4 of 9 layers of it. And in addition, for ease of observation, the foil cover on both sides of fire barrier was not installed. So after the test, here are some data for comparing the started and double slip track. So these are the walls on level 5. Wall 4 is started slip track and wall 5 is double slip track. And these two walls can slip during the test. So both of the slip joint were as expected. But however, the double slip check, the end gypsum cover panel were damaged. So after slip, the end panel will just collide into the outer top check. So we can focus on this part. So the end panel damage. And these type of damage were found at every double slip check wall. And here is the comparison of the slip detail that we connect the wall 10, the partition wall, and wall 14, the shelf wall. So these two walls can move almost identically. So from here is the cut here. So this side is the conventional wall, and the other side is the shelf wall. And next, we will discuss about the effectiveness of the expansion joint. So the first one is the FWFC joint. So from this video here is the wall 9 and the other side is wall 12. And these two walls slip independently during the same motion. So which means that the different movement of the wall were accommodated by the FWFC joint. You can see that. So we can see that the joint just open and close. And the other comparison of FWFC joint is on level 5. So wall 5 is the wall with the expansion joint. It can slip in both directions. But for wall 1, there's no expansion joint here between the wall and the stair. So it can just slip in one direction, but slip a little in another direction. See that? And this is another type of expansion joint on level 6, the AFWC joint. So these we can see that all the wall 15 were measured during this mid 81 motion. So these joints effectively accommodate the incompatible movement in the corner region. So we can see in this video. And due to lack of sensor on these walls, we can just see the effectiveness of barrier from this video. So we can see these two walls slip. And the barrier accommodate the different. And for this slide is the drift reductions for interior walls. So we can see that the drift reduction for wall 2 here, this one, and wall 9, this one, and wall 16, this one, were lower than expected. They are not higher than 30%. But however, there were no construction errors were found. So we think that the low drift reduction might be because of the friction force at the top of the track that prevent the wall to slip. Then here are some damage that we found after the test. So the first damage is what I just said. For all the double slip track, the end of wall panel damage. So this can be prevented by trimming the end of the wall gypsum lower than the upper check. Then another damage is on wall 8. The screws were completely pulled out. And we can increase the number of screws to the design specification of 16 inches on center rather than 32 inches on center to avoid this damage. And on level 4 wall 9, the end corner bead were completely damaged after the test. And this is because we didn't leave the gap between the slab and the wall. And the damage on wall 11, the end of the wall start to crack and the mud around the door crack. And at the beam opening corner here. So we can see that after the test, there's a seriously damage here. The cause of this damage is that wall 11 was not separate from the implant movement from the adjacent wall. So here shows that we didn't install the fire barrier here. And this is not really a damage, but the fire barrier just fell out of the gap. And this is just because we cut off some of the layers of fire barrier and we didn't install the cover on both sides. Then this one is the damage on wall 1, which the wall we didn't install the expansion joint. So after the wall slid, it collided into the stair hardwares. And the last damage we found is on level 6. The expansion joint were bent and pop out due to the bidirectional movement putting torque demand on the joint covers. So here are the lessons that we learned from interior walls. So the first, the slip check and the double slip check work well in most of the wall during the shake table test. Second, the detail of tying the intersecting partition wall and the shelf wall together work perfectly. Third, the performance of the wall appears to be sensitive to the constructions. The next, all the expansion joint accommodate the movement across the corner. And most of all the physical damage observed in these tests are readily repairable. So which means these damage we can categorize these damage as a minor damage. So here are the conclusion and future work. So the conclusion is that the detailed horizontal slip joint can significantly reduce the storage drift transfer to the wall, but the construction detail need to be careful. Yeah. And second, the vertical expansion joint can accommodate the incompatibilities at the corner. And third, the low damage overall, but the system were not, so which means that the system were not tested to their limits. So for the future work, because then we found some of the wall did not slip during the test, which means that varying levels of friction on top track determine the extent to which the wall slips. So for our future work is to set up a numerical model to explain the wall slip mechanisms. So here are the industry partners and sponsors. So thank you for your attention. So this is my presentation.
Thank you, Ian, for the presentation. It was super informative. I'm sure everyone here found it the same. So I would like to open the floor for question. Anyone who has question, please raise your hand, or if you are online participant, just please drop it in the chat box. So as I saw in your slide, the concentration of damage was on the higher part of the walls, not in the lower part. Is there any specific reason for that, or?
You say the higher part?
Yeah.
Is that
these? Yeah, exactly.
Yes. So this damage is because let me show the mechanism here. And So you will just add the higher part because the top panel, the top wall panel just collide into the top track after the wall slip. So it will appear at the top of the wall.
Thank you. Any other question? Please.
Yeah, and after all you've seen, which approach do you think works better, the double slip or the slotted slip?
So after for the test, I think the slotted slip is easier. It can slip more easier because the construction it just need to be careful not to tighten the screws too tight to the slab. Yeah. But for double slip, sometimes because if we didn't tell the constructors, they might screw the screws through both track.
Yeah, you go to that slide of interior walls that shows the statistical performance drift reduction for all the interior walls. Yeah, so you don't have as many slotted slip walls in this one, but
Yes.
yeah, which one? In this, which do you think performed better?
For this one, we can see that the shuffle is it performs the best because we didn't screw anything there. And for a double slip check, so it shows that a variety of slip there. So what I can because like this is it doesn't slip and we cannot find any constructor errors for it. And the most it can just slip like 70% just as double slip track wall. Yeah. And others like just 30 to 40%. So I cannot really tell that double slip track wall is it can slip more better than the slotted slip track. But the construction for these two details is different.
Yeah, the slotted slip is definitely a little easier to construct.
Yes.
More, I think goes together much like the typical interior wall, what they're used to building. I think in the whole experiment, it's just very struck by the variation that we saw of performance in different walls and unable to explain a lot of it, why it occurred. So that's disappointing that we don't have an answer.
Okay, anybody else?
Thank you for the presentation. Actually, my question is a little general and about the cost of the, let's say, the maintenance or the repair of the joints that you're trying to use. These kind of joints, since they're, I guess, stainless steel, they don't need to, we don't need to be worried about the corrosion or something like that. But let's say after the failure, if failure happens, is the repairing those joints or replacing them would be convenient or it would be too expensive? Have you any idea about that?
I don't know if it will, I think it will not be too expensive to repair because those joints were just installed. Let me find construction. So for these joints, we install it after the framing, so we can easily to repair it. So just like if the gasket here just damaged, we can just tear it off and then put another new gasket in there. So it is really so we don't need to do anything with the wall framing or the maybe gypsum something. So we just need to repair the expansion joints itself. So I think it's easy to repair, and I don't think it costs a lot.
Joints were the most reliable part of the whole mechanism. The slip joints at the top weren't, but all the expansion joints worked as they were supposed to, so they should be fine.
Okay, any other question? Go ahead.
Testing. How long did it take to build that massive timber structure before you were able to actually test all this?
it takes like for the full building, we build like half year and more, and then we install all the sensors like 2 months more. Yeah. So for the full test building, we spend like a year to complete this test.
Okay.
Worth pointing out that construction was slow because of the small footprint of the building and the fact just limited space to work with. We couldn't have multiple trades working at the same time. So, I mean, it was really a challenging construction project and took up a whole bunch of time on the table because of that. Yeah, but the actual wood contractor, I think they say about 4 months of total time on the main structure, and then all our trades were another 4 months probably.
Any other question? Okay, so just before wrapping up, thank you again for being here today. And as a quick reminder, we have pizza, so just make sure to grab a slice before leaving and have a great day. Thank you again.